Hello, my name is Christian Bester and I am currently studying computer engineering at the University of Pretoria, and I am also a vacation work student at Opti-Num Solutions. In this webinar, we're going to discuss software-defined radio deployment on system-on-chip platforms using MATLAB and Simulink. This webinar was adapted from a webinar which was originally done by MathWorks and Analog Devices. I will first highlight the challenges of designing software-defined radios, and then we will look at a workflow which deals with these problems. We will then work through each step in the workflow by using an example. Once we are done with the example, I will talk about how you can use MathWorks tools for a wide range of hardware devices, as well as the next steps you can take to use the tools and workflow in this video for your own project. First of all, for those of you who aren't familiar with the concept, software-defined radio is a radio communication system where components that are usually implemented in hardware are instead implemented in software running on a computer or embedded system. At one time, and maybe in your own lab now, this was radio development, lots of wires, boards, and outboard test and measurement equipment. Add to that all of the disciplines and skill sets required to bring a software-defined radio to market, which is very often not available to any single company, making it a daunting task due to the added difficulty of cooperation between the various engineers and design teams. That is why MathWorks and Analog Devices aims to make the design process more efficient by providing a platform for development and testing which allows technical communication and cooperation between the engineers and design teams required to bring an SDR into production. The design methodology that allows for this type of cooperation is the model-based design workflow introduced in this slide that starts with modeling and software simulation, adds in testing with real-world data, and then moves to hardware deployment, all within one environment. We will be discussing these steps in more detail as we go along. The workflow showcased here consists of 4 design phases and 5 hardware verification steps, all based on one golden algorithm reference, one set of requirements, and one test infrastructure, and that's where we gain our development efficiency. Here we see a graphical representation of our 4 design phases. In the system architecture phase, we validate components, perform a full system simulation as a proof of concept, and set the requirements that will be used for validation throughout the development process. In the requirements verification phase, we define our radio through MATLAB algorithms based on our requirements and verify that our algorithms meet real-world data specifications by testing the algorithms on the hardware validated previously. Next, we use Simulink for detailed design of a good hardware implementation of our radio. We can then enter the deployment phase using code generation tools to develop a prototype and finally integrate additional system elements into a production radio. In our example, our design is based on the AD9361RF Agile transceiver from Analog Devices, which is used by all the hardware platforms in this video. Let us start with the system architecture phase. Component evaluation is done by using pre-built software to determine whether the selected device meets design requirements, as can be seen in this screenshot for our example where Analog Devices IIO oscilloscope captured data from the AD9361 transceiver. Simulink can then be used to do an end-to-end system-level simulation to verify that our chosen hardware and proposed algorithm meets system specifications. This is an end-to-end model of our proposed system where we generate the message in the QPSK transmitter, send it to our AD9361's transmitter, where it is transmitted over our transition channel to the AD9361's receiver, and then output to the QPSK receiver, where we can see the message in the diagnostic viewer once we run our simulation. The first few strings that are being received as garbage since the data is still unstable. We can also inspect our constellation diagram, our transmit spectrum, as well as our receive spectrum. And here we can see messages being received block for block. Note that the simulation is application specific. However, you can use your own transition channel and transceiver models to test the system you want to develop. Now that we are done with the system architecture, we can start building specific algorithms to meet system requirements by moving on to the requirements verification phase. Here we create our algorithm reference model, where our primary goal is numerical accuracy, as this model will be used for verification throughout the rest of our design process. That is why we use MATLAB for accurate mathematical operations and vector manipulation. We then need to verify our model using real-world data. I have a Pluto SDR device connected to my laptop, and MathWorks and Analog Devices have created this MATLAB script, which basically runs an end-to-end test of our example system by generating data which is transmitted by one antenna of the Pluto device and received by the other. The whole idea of this test with the Pluto is to make sure that our algorithm reference model works correctly when working with real-world data. Here we can see our various constellation diagrams for different parts of the system simulation, as well as our spectrum analyzer. And once our simulation has completed, we can see the graph of our total errors versus the samples that we tested, and we can also see that 0 errors have occurred during our entire simulation, which indicates that our algorithm reference model is working correctly. Now that our reference algorithm is verified, we can move on to our detailed design phase. This phase is our first step towards hardware deployment, where we need to convert our vector-based approach in MATLAB to a scalar-based system. We also need to target programmable logic by converting to fixed point operations, looking at efficient hardware utilization and data flow architectures, and finally moving on to HDL code generation. The perfect tool for these tasks is Simulink. You may be asking, why Simulink? First, Simulink gives us a concept of time. It allows us to explore algorithm architectures in a modeling environment, and it serves as a common language for the various design teams due to its ability to model algorithms and components, which allows easier communication and cooperation. We can use Simulink to create a floating point scalar-based system from our algorithm reference model, and then move on to fixed point to generate HDL code. Because our aim is to move on to HDL code deployment in the development phase, we need to elaborate our design for efficient hardware implementation by making our design more hardware friendly. So far, we have only cared about the mathematical accuracy of our operations, but now we need to look at implementing them efficiently in hardware. You can utilize our fixed point designer tool to convert your floating point system to a format that is HDL code generation capable. The functionality of our Simulink models should be verified against the previous working model, eventually going back to our algorithm reference model. Now that we have concluded our detailed design phase, we can start looking at designing a prototype running HDL code. To test our algorithm reference model, we use the Pluto SDR to generate and capture data, which is an inexpensive device that uses the AD9361 transceiver. We would now like to move to a larger FPGA for prototyping, specifically the Analog Devices RF System On module with FMC breakout board, which uses the same transceiver as the Pluto SDR. We can now use our fixed point model from the detailed design phase to generate HDL code for our prototype. You can use HDL Coder and HDL Workflow Advisor to generate the code and optimize its performance for your prototype. We should then verify the functionality of our prototype against our fixed point model. Once we know that our prototype works, we can then move on to our final hardware verification step. We can now easily move from our prototype to a production radio, which also uses the RF System On module and the exact same HDL code, but on a custom carrier board with added functionality. Now that we have finished our final design phase, let us look at the software and hardware flow of our design process as we progress from one design phase to the next. The great thing about the model-based design workflow we are showcasing here is the fact that from the beginning of the project up until the point where you have a fully working prototype, you are working in only one environment. It is because of this that MathWorks tools enables easier collaboration between team members in an SDR project, reducing development time significantly. In our example of the model-based design workflow in this video, we made use of hardware using the analog device's AD9361 transceiver. However, MATLAB and Simulink are not tied to any specific hardware platform. With the help of our hardware support packages and various custom reference designs, you can use the model-based design workflow to enhance the efficiency of your own hardware-specific radio project. At Opti-Num Solutions, we can help you get the software tools you need to get started on your own project. We also have various courses on how to use these tools effectively, and on top of that, we have an entire team of competent consultants who can assist you with your own project. The next steps that you can take, if you are considering our offer, is to go to the MathWorks website for an overview of available SDR Workflow solutions, and as well as the Analog Devices website to explore RF transceivers. On our own Opti-Num website, you can download a trial, ask for support, or check out our SDR Workflow page on our Tech Corner. Thank you very much for your time.